In this video, we're going to be talking about Faraday's law. We're first going to start off with Lenz's law, which is just showing us the direction of an induced current. So say we have a magnetic field that's going into the page like this, with a loop around it. Say that this magnetic field is growing larger into the page. This would therefore mean that we'd have to have an induced magnetic field that's coming out of the page at us in order to counterbalance this one. This would create a movement in charge, or a current. And from Lenz's law, we can tell from the right-hand rule that the current is going to be going counterclockwise around this loop. Now, this is just Lenz's law. Now, Faraday's law tells us exactly how we can get these induced currents, and therefore an induced EMF. So Faraday said that there are three ways to produce an induced EMF. So let's start off with just a simple equation. Magnetic flux is symbolized with a capital Phi. This is equal to B, or the magnetic field, dotted with A. Let me rewrite that. B dotted with A, which is just the area. So Faraday talks about an EMF, this squiggly E, equaling the change in magnetic flux over the change in time, and the three ways that this can happen. So let's start off with just the change in magnetic field. So for instance, just like this loop above, we have a magnetic field going into the page that is gradually getting larger. Therefore, we have an induced magnetic field coming out of the page, an induced current. So this just simply means that there's going to be a change in current, which is voltage. So this is equal to dB dt dotted with A. So the change in magnetic field over the change in time times the area, which is unchanging. Now, the second way to do this is a change in area. So we have a constant magnetic field here, and we have a square loop that's outside the magnetic field right now. So it has a zero EMF because nothing is happening, there's no movement here. Now the loop starts gradually moving in towards the magnetic field. So in a few seconds, this loop is going to be over here and be completely full. So the area is now changing and causing the movement of charges and making this magnetic field larger, making an induced current and an EMF. So this one is dA over dt dotted with B. This just shows change in area over change in time times the magnetic field. Now, in order to get the next one, we need to go up here to the original equation for magnetic flux. We know that dot products is just these two times the cosine of theta in between them. So this is just BA cosine theta. So the next one is a change in theta, which would affect both the magnetic field and the area. So say we have some device that has a little half circle on it that has a crank arm, and this crank arm moves this and spins it at a certain frequency. And now we have a magnetic field that's going through this, but as time goes on, this just continues to move. So at some time, the half circle is going to be up here with no magnetic field lines through it. Sometimes it's going to be perpendicular to this, again, no magnetic field lines. So the theta of this device is changing, and the theta is affecting both the area and the magnetic field. So we note this as d dt times cosine of theta times A times B. This therefore means sine theta because we know that the derivative of cosine is sine theta. So when we plug this in, we'll probably just plug it in like this, but note that dt of cosine theta equals sine theta. So we'll plug this in as AB dt cosine theta. So this is the three ways, and this is why Faraday says there are three ways to change the magnetic flux and therefore get an induced EMF. So first is change in magnetic field, then change in area, and then change in theta. If you want to plug these in and solve problems, if there's a change in magnetic field but no change in area or theta, these will both end up being 0. But if area is just changing, it'll do the same with the magnetic field and theta, and the same for theta, that magnetic field and area would be 0. So ultimately, the change in magnetic flux equals all of these separately, but you can add them together since they'll be 0. But that's it for Faraday's law. It just gives us a more specific answer rather than Lenz's law, which just gives us the direction.